let me remind people that we do have a scheduled talk at 3 o'clock today. But that's not until 3 o'clock. So right now, our speaker is Michael Rappoport from Bonn, and he will talk on the p-adic uniformization of Shimura curves. Michael, whenever you're ready.
Okay, I'm ready. So
all right.
Thank you very much for the invitation to speak. It's a great pleasure to speak at the birthday party of Steve Kudler. He will actually enter only later in my talk. So let me start. So throughout my talk, the notation will be the following. So F is a totally real field. And I fix two places, one which I call W, which is an Archimedean place, and one p-adic, which I call V. Okay, and so let me start by going back to 1976. So many of you were maybe not born even at this time. And there were two theorems which are remarkable and which are relevant in this context. And let me start with the first one, which is by Gerardnick. So I heard that the idea to this theorem is due to Manin. And so Gerardnick does the following. He considers a Shimura pair Gx, where G is the algebraic group associated to the multiplicative group of a quaternion algebra. So D is a quaternion algebra over F, with the following conditions. So first of all, for the Archimedean primes, we have that if we localize at this Archimedean prime, then this is either the matrix algebra, if W prime is equal to W, and it's a Hamilton quaternions otherwise. So in other words, this quaternion algebra is non-split as at this distinguished Archimedean place W, and it's split at all other primes. Okay, and for V, we assume that it is ramified. So this is a division algebra. So this is the first pair, so this is G, and then X is the obvious one, the obvious datum, namely at the prime W. It is the usual thing that we use when we talk about the modular curve, and at the split. Sorry, is this readable actually? Oh, so it's not automatic. Sorry. And at the other primes, it's just the trivial homomorphism. Okay, and then we have associated to this a Shimura variety. Which you write as the usual way as G of Q divided into the product of X and G of the finite adults of G modulo K, where K is an open compact subgroup of the finite adults. And if we unwind this, so X becomes here, is made into a complex manifold. This is just a disjoint union, finite disjoint union of quotients by arithmetic subgroup of omega R, where omega R is the union of the upper and lower half, sorry, of the upper and lower half plane. So in other words, it is the projective line over C minus the projective line over R. You will see immediately why I'm writing it in this way. And now let's consider the following condition on this open compact subgroup. Namely, it should be of the form K away from P times K at P, where K is at P is the unique maximal compact subgroup of G of FV. So, I mean, maybe it's better to write this of the multiplicative group of the quaternion algebra. Okay, and then the theorem of Geretnik is the following. First of all, this Shimura variety has a canonical model which I would denote with an index F over F, which we consider as a subfield of C by this fixed Archimedean prime W. And furthermore, if K satisfies this condition star, then we have the following isomorphism. We extend scalars from spec F to spec the completion of the maximal unramified extension of the localization at W, at V, sorry. This is isomorphic to the following double quotient. So I will explain in a minute what this means. So I have this thing here, and then I have G of AF V. Sorry, no V. Modulo K. Okay, and let me explain the notation here. So G bar, this is the castling of G, namely, it is the multiplicative group of the quaternion algebra D bar, which coincides with D locally at every prime, except for these two distinguished primes where the roads are interchanged. So in other words, this D bar at W is a Hamilton quaternion, and the D bar at V, this is now the matrix algebra. And furthermore, what is this omega FV? This is the Drinfeld upper half plane. Namely, it is a projective line over FV, where you remove all rational points of, sorry, not this. All rational points over the ground field FV. So this is a rigid analytic space of dimension 1. And the interpretation of this theorem is the following. So on the left-hand side, we have an algebraic curve, which is defined over the over FV breve. And if you take the associated analytic space, then you get the analytic space that is written down on the right-hand side. So this omega is a rigid analytic space over FV, and then you extend scalars in the rigid analytic sense, and you get this rigid analytic sense on the right-hand side. And this has an expression which is very analogous to what we met over the complex place, namely the right-hand side can also be written as a finite disjoint sum. Okay, you have to extend scalars for every breve, where gamma I bar, these are some subgroups in PGL2 FV, which are discrete and co-compact.
Mikey,
Yes,
yeah.
I don't hear you.
Sorry. How does G bar act on G of AF? Do you mean the Adels away from the place V?
Okay, very good question. Indeed, this action does not come from an injection of G bar of Q into G of AF. But remember that at the place V, this quotient is actually very trivial. Maybe it's just the integers. And so this action just registers, in some sense, the valuation of the determinant. Are you there?
I'm here. I'm here. Thanks.
Okay.
Thanks.
Okay, so let me make some remarks. Remarks on Gerardnick's theorem. So first of all, let me point out that if F is not equal to Q, this is a bad Shimura variety. In the following sense. So first of all, it is not of PEL type. In other words, it doesn't parameterize abelian varieties with additional structure. It's not even of Hodge type. Secondly, the weight homomorphism that we always have associated to Shimura variety, which goes into the center, this is not defined over Q. Oh, sorry, not defined over Q. So it's the Linus philosophy that for Shimura varieties where the weight homomorphism is defined over Q, then this should be a moduli space of motives. So in this philosophy, we cannot expect this Shimura variety to be a moduli space of motives. And secondly, and finally, the Q split, the maximal Q split torus in the center is not equal to the maximal R split torus in the center. And this means that you have no hope of constructing local systems in the natural way on this Shimura variety. And then there's another thing that is sort of problematic about this Shimura variety, namely, there's no proof in Gerardnick's theorem, in Gerardnick's paper. Okay, there are some remarks about what this means and so on, but there's no proof. Actually, the situation, I will comment on this a little later, the situation is a little better because in 1995, there was a preprint by Bouteau and Singh in which they gave a proof of Gerardnick's theorem by reduction to other uniformization theorems. But unfortunately, the paper was rejected by the referee, who said that it doesn't contain enough new things. Well, I happen to disagree with this. Okay, so that's the first paper in 1976. And now let me talk about the second paper. So Mani explained to me that he gave his two students, Gerardnick and Drienfeld, each other's paper to read in order for them to improve their writing style. And so Drienfeld thought about this thing, and he considers the case where f is equal to q. And so in this case, he shows that this canonical model, so this is now over Q, that this represents a moduli problem. Namely of special abelian OD varieties. So roughly speaking, abelian varieties, which are of dimension 2, which are equipped with an action of the ring of integers in this quaternion algebra, and that satisfies a certain condition on the Lie algebra. And furthermore, he extends this to a modular problem. Modular problem, not simply over Q, but over the localization of Z at P. So let me call this A, maybe with an index K. And he proves that if you take this modular problem and you extend scalars from spec ZP to spec the integers in this maximum completion of the maximum unramified extension, then you can write this again as a double quotient where you have a formal scheme. And so you have to write spiff instead of spiff. And then you have the same quotient as before. So in other words, here you have G of AF modulo K. And so here the interpretation is in terms of a Gerardnick's interpretation. So on the left-hand side, you have this projective scheme of relative dimension 1, and you can take its formal completion along its special fiber, and you get a formal scheme, and this formal scheme can be identified via the right-hand side. And what is this omega hat QP? This is Drienfeld's formal scheme, formal model of his p-adic half plane. So in other words, if I take the rigid analytic space, which is, so to speak, the generic fiber of the formal schemes on both sides, then I can leave out the hat because I get back Drienfeld's upper half space, Drienfeld's half space, and I get back this assertion of Gerardnick's theorem in this special case where f is equal to q. So let me make some comments on Drienfeld's theorem. So first of all, this is a good Shimura variety. In other words, everything I said critical about Gerardnick's Shimura variety is not true. In other words, it is a PER Shimura variety. It has a good weight homomorphism and so on and so on. Although it has bad reduction, of course, because this former scheme, omega hat, is not a formally smooth former scheme, but it has singularities, but that we control. And secondly, this paper of Drinfeld contains a complete proof. Although the proof is extremely brief, I think it's only 6 pages long, and there have been several more complete expositions of this, although these expositions are the same proof. And the proof is actually very difficult, which is in some sense regrettable, because this theorem of Drinfeld is of very high importance. So until the beginning of this year, it was actually the basis of the theorem of Falk-Fontaine, in which they classify vector bundles on the Falk-Fontaine curve. So at the beginning of this year, the situation changed because Falk and Schulze have in their new papers, they give a new proof, which is based on Banach-Corness spaces. The main part of the Drinfeld's proof is the study of a formal modular space, of p-divisible groups. And it was the starting point. In some sense, this is the simplest Rappaport zinc space. And it was actually the starting point for constructing these spaces. And nowadays, it has gone on to construct local Shimura varieties and their integral models. So it is actually an extremely important paper, even from the point of view of history, I think. There have been generalizations of Drinfeld's theorem. One is to higher dimensional Shimura varieties. So this is in my book with zinc, in which we single out certain higher dimensional Shimura varieties which are attached to fake unitary groups and prove for them p-adic uniformization. But another, so I don't want to talk about this except to say that this proof of Buteau and zinc, this is by reduction to fake unitary groups, and then in the end to our book. So I don't want to talk about this, but rather I want to explain a variant of Drinfeld's theorem, which works for Shimura curves, where the degree of f over q is bigger than 1. Okay, so this is my next section. And since I started by naming the first section 1976, I will name this thing here 2012 to 2020. And this is joint work with Steve. And zinc. And so I'm going to explain how to construct Shimura curves which are of PEL type and which have behavior which is very similar to what Gerardnick has. So before I say this, maybe I should explain why these 3 names together. So, I mean, I think that by what I said so far, you will not be so surprised to find zinc and my name here. But Steve may be surprising. And indeed, the origin of this theorem is very strange. Namely, Steve and I started out trying to study Kudla-Rappoport divisors when the length of the vector defining them is equal to 1. So this is exactly what Ben Howard did, except that he did this in the case where the prime was split. And when the prime is inert, as we were supposing, things get much more complicated. And we didn't really solve this problem, but by making this calculation, we made a very striking observation. Namely, we seemed to find the Drinfeld half space in this problem. And so we proved this theorem, which was called an alternative interpretation of the Drinfeld half plane. And I talked about this in 2012 in Bombay. And on the party afterwards, Tiluin came up to me and he said to me, surely you're doing this because you want to prove a global theorem. And this was very embarrassing, but we had not thought of this. And so since during these 8 years, we worked on trying to prove a global theorem about this. And so we have succeeded to some degree, so that's what I want to explain next. So I will denote by K a CM extension, so totally imaginary quadratic extension of F, and I will denote by V a two-dimensional K vector space, and psi will be an alternating form, Q-linear alternating form, such that psi of AX, Y is equal to psi of X A bar Y if I take an element in K. And furthermore, I denote by phi the set of algebra homomorphisms from K into Q bar, and I let R be a generalized CM type of rank 2, which is special with respect to this Archimedean place W that we have fixed for F. So what does this mean? This is a homomorphism. This is a map, not a homomorphism, a map from P into Z, the non-negative integers, which sends phi to an integer R phi, such that the sum of the value at phi and of its complex conjugate is equal to 2 for all phi. And then the special condition means that if I take these two complex embeddings, which correspond to W, that they should be equal to 1. And also the other ones, the other phis should be either 0 or 2 for all phi not equal to phi 0 or phi 0 bar. Okay, and then we make the same assumption as Gerardnick, namely we assume that V is non-split in K, and that the invariant is equal to, of V at this distinguished place is equal to -1. So in other words, we are again making this assumption that this is a non-split situation. And now we take the group of similitudes for this form, and there's an obvious second part of the Shimura datum, which depends on this generalized CM type that we have fixed. And we have associated to this a Shimura field, so a reflex field. So this is a reflex field of R. So in other words, the Galois group are all those elements which preserve this function R. And then because we are assuming that this is special at V, we see that F is a subfield of this Shimura field. So this might be a bigger field, which is in some sense the blemish of our result. Okay, and now we fix a place of this reflex field which lies over this F under this injection. And then again, this Shimura variety this has a canonical model over ER. And furthermore, it represents a moduli problem of polarized abelian varieties with action by the ring of integers in K. So in other words, it parameterizes tuples where we have an abelian variety of dimension 2 times the degree of F, where iota is an action of the ring of integers. Then we have a polarization lambda such that the Rosati involution of lambda induces on F complex conjugation. And finally, we have a level structure modulo this open compact subgroup K that we have fixed. Okay, and so this is a good Shimura variety. In other words, unlike Gerardnick's Shimura variety, it has all good properties, weight homomorphism defined over Q and so on and so on. And now we make an assumption which is analogous to this assumption star that appears in Gerardnick's theorem. So we take K to be of the form K prime to P times K at P, where K at P is contained in the p-adic points of this group, and we take this to be defined as follows. So we fix for any prime of F dividing P, we fix the lattice lambda P in the localization at P of V, such that if P is split or ramified, then lambda P is self-dual. If P is unramified and the space is unramified, so in other words, the invariant is equal to 1, then we also take this to be self-dual. And if P is unramified, but the invariant is -1, then there doesn't exist such a lattice. And so we take this to be almost self-dual. So in other words, then lambda is contained in its dual, and the co-length of these two lattices is equal to 1. And then by Kp, we mean the common stabilizer of all these lattices. Okay, and then again, we can define a modular problem. Which I will denote again by AK, which now is over spec of the integers of the reflex field at this prime that we have fixed. And the theorem now is the following. So first of all, the model that we get by taking this modular problem, this is flat and has semi-stable reduction, just as in Dringfeld's theorem. And secondly, we have an isomorphism of formal schemes where we take the completion of this this model along the special fiber, and then we again extend scalars to the completion of the maximum ramified extension. And then on the right-hand side, we get the exact analog of Dringfeld's theorem. Namely, we have here the castling of the group that divides into omega f v hat, and then extended scalars from fv into spiff O mu Rewe, and then again G of AF modulo K. So let me make some comments on this. So first of all, as in Dringfeld, this is deduced from a theorem on p-divisible groups. But more goes into this. Namely, so let's go back to this definition of this modular problem. So here we have an abelian variety, we have this action of OK, and then we have a polarization lambda, where we will impose on this polarization, so in modular problem. So first of all, we have to make sure that the Lie algebra behaves well, and this is given by the Kottwitz condition. Which depends on this generalized CM type. Namely, if I look at the characteristic polynomial of an element, maybe I shouldn't call it X. Maybe I should call it I don't know, X. And this should be equal to the product of T minus phi of X to the R phi, where phi runs over all these embeddings. So this is the usual way in which we can ensure that we don't get extraneous components in characteristic P. And secondly, of course, I mean, so we have to impose such a condition already over the complex numbers. And also we have to make an assumption about the kernel of lambda. Namely, if I localize this at a prime P, then I want that the order of this thing is equal to the order of lambda p hat modulo lambda p. So these conditions I have to already impose in characteristic 0. But now remember that we are here in the case of bad reduction. And if you think back at the way Kottwitz defines his modular problem, he's in the case of good reduction. And so here we have this problem that over the complex numbers, we are imposing here it is. We are imposing a level structure. We are imposing a level structure which involves also the Tate module at P. And of course, this is pathological in characteristic P, so we cannot do this. In the case of Kottwitz, he doesn't have to do this because automatically there's only one way of doing this. But here, this is different because we are in the case of bad reduction. And so there are two more conditions we have to impose on these on this modular problem, namely the sign condition. This ensures that if we drop the prime to P, I mean, no, the P primary component of the level structure, that in characteristic 0, we do not get more components. In other words, that in characteristic 0, we can recover the level structure also at the primes above P. And then there's another problem that one always has to fight with when one extends a modular problem over the integers, namely this is flatness. We have to make sure that they are not extraneous components that only live in characteristic 0, that only live in characteristic P. And this is a very complicated condition. It's called the Eisenstein condition. I cannot go into details here, but in any case, by imposing all these conditions, we prove that this gives actually a flat model. And how then is it proof that we have p-adic uniformization? Well, p-adic uniformization there are two proofs. There's one proof which is very abstract, which is by Schulze and Weinstein in their book. And they use integral p-adic Hodge theory. And roughly speaking, what they do is they start from the generic fiber, which looks a little bit like Gerardnick's theorem, and then extend to the special fiber. So this is a very sophisticated proof, I think. And our proof this does not use p-adic Hodge theory, but it uses the theory of displays. And so this starts from the special fiber. And then extends to the generic fiber. Okay. Okay, maybe This is as much as I want to say. Maybe I should also say that this implies, again, a version of Gerardnick's theorem. Because this, this group GU is very closely related to the multiplicative group of a quaternion algebra. More precisely, these two differ just by a torus, and in this way one can deduce Gerardnick's theorem from this theorem, from this p-adic uniformization theorem. Now we share the problem with Bouteau-Zink, namely our paper was also rejected, and the referee said it doesn't contain enough new thing. Actually, I suspect that the referee in both cases was the same. But I hope that eventually it will be published, and then we will finally have a proof of Gerardnick's theorem. But there is actually a snatch in this, namely, if you compare Gerardnick's theorem with ours, then you will see that in our case, so Gerardnick, he fixes only KV, which is the maximum compact subgroup, and this K upper V, this is free to vary. Whereas here, so this is Gerardnick, whereas we fix KP, and we take this in some sense maxima, or at least, I mean, it's so to speak a fixed thing. And we are allowed to vary the open compact subgroup prime to P. And of course, this is in some sense not so nice. So let me say something about something that we're working on, namely, we use a slightly different Shimura variety, which actually came also up in Ben Howard's talk. So we fix the classical CM type to a half system of complex embeddings. And we call P0 to be the one of these two special embeddings which lie inside P plus, and such that if I take all those p's where the value of our phi is equal to 2, and this is equal to phi plus minus P0. So there are two possible choices. For phi plus. And once I make this choice, then I can associate a trivial Shimura variety, which, as I said, also came up in Ben Howard's talk. So in other words, we take this torus in restriction of scalars of k down to q of gm, such that the norm lies in q. And then we form the group G tilde, which is equal to ZQ over GM and G. So in other words, we take this set of pairs such that in both cases, the two multiplicators coincide. So this group is also considered in my paper with Smithling and Zhang, and it's easy to see that you can write this group in a canonical way as the product of ZQ and the unitary group associated to V. And then we again get a Shimura datum in the obvious way, and it maps to our original Shimura datum. And these two differ just by a torus. And the Shimura fields behave the other way around. So the Shimura, the reflex field for this tilde Shimura variety is an extension of the Shimura field for this other Shimura variety. And this degree of this extension is at most equal to 2. And then again, it's easy to show that this is a good Shimura variety. So this is a good Shimura variety. And it has a canonical model over E tilde, and it again represents a moduli problem. Of abelian varieties which are polarized and with an action by OK. Okay, and now it is easy to see that here we can take this K tilde. So we will take this K tilde of the form in terms of this decomposition as a maxima compact subgroup, open compact subgroup of this torus times an open compact subgroup in the unitary group. And here we can now take this Kp tilde, we can take this now to be free. So in other words, we can write this as, first of all, a part which is prime to P. Then we can write a part which is at P, but prime to V. And then at the place V, we just take the unitary group. So I mean, so maybe I should say Ku, sorry. So this is Ku. So this Ku. And then here we just take at P, we just take the unitary group at Fv, which is an open compact subgroup. Okay, and then in this case, we again get a new model over spec OE twiddle and some place U tilde that we fix. And again, we have these 2 points, namely it is flat and semi-stable reduction. And we have p-adic uniformization, which is now in complete analogy with Gerardnick. Okay, let me conclude with some remarks comparing this to Gerardnick's theorem. So what is good about this is that these Shimura varieties, they are in some sense better. I mean, as I explained, I mean, not only by their formal properties, but also by the fact that they represent the moduli problem. So in other words, we really know how they reduce modulo the place that we fixed. And in fact, one can also, I mean, I only wrote down this isomorphism of formal schemes over this Breve space. In other words, after passing to the maxima and ramified extension, but one can also write down the descent data on both sides. And therefore, one has a completely explicit expression of an integral model of the Shimura variety one started with. This is what is lacking in Geretnik's theorem. On the other hand, Gerardnick's theorem has the advantage that the reflex field is as small as possible. So in both of these Shimura varieties, you saw that these fields E, respectively E tilde, they are bigger than F. And this has actually some importance if you want to think about arithmetic questions, global arithmetic questions. On the other hand, it is our hope that our theorem has other arithmetic applications, maybe in the local case, like bounding Selma groups or level lowering or level raising, as has been done in Geretnik's theorem when the local field is QP in the hands of Rivet, Bertolini, Darmon, Nekovar, and many others. So I think that maybe there is some use for some practical use for this. And let me now finally conclude with one remark, namely, in all these cases, the right-hand side is a finite discharge union of spaces of the form gamma bar divided into omega, some local field, where gamma bar is in PGR2FV is a discrete co-compact subgroup. And the function field analog, actually there are two kinds of uniformization. There's one which is completely analogous to this one here, where the Shimura variety or this variety of Stukas or of elliptic modules has bad reduction. But on the other hand, in Drienfeld's first paper, he also has a different uniformization. Namely, he has fixed a place which he calls the Archimedean place. Of course, it's not an Archimedean place. And he proves an analogous uniformization theorem where now gamma bar, so in Drienfeld function field case, he has omega f infinity divided out by gamma bar, where now gamma bar is a subgroup of finite index in maybe PGL. In PGL OF 1 over infinity. So a finite index. So in particular, it is not co-compact. This question came up in Darmon's talk because he said, I mean, he was lamenting the fact that we don't have such examples in the function field, in the number field case. And a long time ago, I asked Drienfeld about this, whether he sees any possibility of creating such a situation in the number field case. And his eyes lit up. It was obvious to me that he has thought about this. And he said, well, let's leave this for the next century. Okay, I think we should be maybe more optimistic because it has something to do with the fact that Scholze was able to construct the analog of Stukas in the local sense. So Stukas come from the function field case. And of course, Scholze is thinking about the analog in the number field case. So far, he has not succeeded. He has only succeeded in the local case. But I mean, maybe Scholze will have a student who will carry the torch on. I would like that. Okay, I'm done. Thank you.
All right, let's thank Michael for a nice talk. And we have plenty of time for questions or comments if anyone has any.
So for this reflex field here, is it automatically unramified extension of the space field at P out of V? Because otherwise, there's your base change in taking base change.
Okay, I mean, I wish my co-authors would look at this. Okay, do I remember? I mean, I did think about this, but I'm not sure actually. Yeah, it may be, I mean, right. I mean, there's one thing one should say. I took this phi plus to be this thing where the R phis are equal to 2. I mean, there are other ways I could vary this. I just did this for simplicity, like in our paper. I mean, so there's this what we call the fake Drinfeld case and the Drinfeld case. And so maybe by doing something more subtle, we can actually arrange this thing to be unramified. But I mean, I didn't think about it. It's some elementary question about Galois.
Right. Yeah.
Right.
All right.
Can I ask a question? So can you say a few more words about how to prove flatness using this Eisenstein condition?
Yeah, that's a very difficult question to answer because maybe I answer this in a philosophical way. I mean, so these Eisenstein conditions, they come out of the blue. I have no motivation for this.
I'll have coffee.
I mean, in general, we have this problem. We can define these, what we call the naive local models, and in general, they're not flat. And
Yes.
so you have to impose additional conditions. And at the moment, it seems that each time you meet an interesting moduli problem, you have to rack your brain to find a condition that imposes flatness. And I have I don't know a good way of going about in this problem. So, I mean, it was just somehow an idea and it worked. And the way one can prove this is, for instance, by using the theory of local models. So
is this supposed to be analogous to like spin or wedge local conditions?
Well, these are other ways of forcing flatness. But this condition is different. I mean, so unfortunately, what I would like to have is one condition which solves all problems. But since we know now many examples, this condition will not be simple, I think. And let me also point out that in Schulze-Weinstein, if you look in this book, they do this actually in an axiomatic way. And so they refer, in some sense, to our paper, which at the time existed only in preliminary form. And there we actually did this flatness by working on the local model. I mean, in the final version, we actually avoid the local model altogether. We prove this directly.
Just by using the Eisenstein condition?
Well, in both cases, you have to use the Eisenstein condition. But the question is, do you go through the theory of local models or do you do this directly?
Sorry, I don't see how you do it directly. Can you say, like, how do you prove flatness without using local models?
Because at the same time, we want to prove this p-adic uniformization. And so this means that you want to relate these p-divisible groups that come up here to Drinfeld's p-divisible groups. And so for Drinfield's p-divisible group, we know that this moduli space is flat. And so we show directly that this gives an isomorphism on moduli problems.
Ah, okay. Okay, thanks. I also have another question. So are there like known examples where the reflex field E tilde is actually, okay, I think you said it's of degree 2 over E, but so in your moduli problem, the reflex field is always big. It's never as small as possible.
Right. I mean, of course, I mean, in our setup, you can still fix this generalized CN type. This has a priori nothing to do with the quaternion algebra. And so by fiddling around with this generalized CN type, you can make the reflex field smaller. This may actually play a role for arithmetic questions like vanishing of the L function and so on. So, but I don't think we have thought about this deeply because I don't know a concrete application of this, but I think this is possible.
Okay. Also, does this your model with Wei and Brian Smithling, like, is your model naturally compared to like Kiss and Papa's model?
Wait a minute, there are two questions here. Well, maybe I misunderstand.
So yeah, like, so I was just wondering if your model, like, if there is a map going from your model to Kiss and Papa's model or the other way around.
Well, I mean, Kiss and Papa's model, this is just given by closure, right? Or normalization of the closure. Then, of course, you don't know what you get. I mean, of course, since ours is flat, it is equal to the closure.
Okay, okay, it is equal to the closure. That's what I wanted to know.
Right, by flatness, right.
So like you didn't throw away some points. It is exactly the closure of the generic fiber. Like you didn't have to. Right. There's nothing that's not liftable to the generic fiber that occurs from your moduli problem.
Right.
Okay, that's good to know. Okay, thanks.
Michael, you may have said this while I was distracted, but your uniformization theorem for really for the integral model, not just the generic fiber, was this only for the unitary group, or can you also do this for the quaternion group?
No, I mean, by unitary group, you mean unitary similitude group.
Unitary similitudes, right.
Right. Yeah, no, I mean, the point is that in Gerardnick's setup, there's not, I mean, what is the integral model? I mean, there is no such thing.
Well, I mean, you can construct one by normalizing in the unitary, the GU Shimura variety, right?
That's what Boutrout do, right?
Right. And then is there a uniformization theorem for that integral model defined as in that way?
Right. This is, I mean, so I have been pressuring Tsing for the last 25 years to resubmit his paper.
Okay.
And, at least I'm so far that he is working on this again, but who knows when. Oh, okay. But I mean, this is what he does in principle. So he formulates a modular problem which somehow is very closely related to this Gerardnick type Shimura variety. And then he does have an integral model, but of course this theorem can never be totally satisfactory because it doesn't compare two things which are given a priori. Because one side in this setup, one side will always be given in some sense by the other side.
I'm not sure about.
I mean, okay. I mean, well, okay. I mean, if you accept the last question, right? There was this question: can you just take the closure? Of course, you can take the closure, and then you prove something about the closure. But in some sense, I don't find this so satisfactory, because when you take the closure, you don't know anything about this.
Well, doesn't Carryall, I mean, Carryall proves regularity, for example. I mean, you know a lot about it, but.
Yes, okay, okay, it's true, it's true. I mean, it's also a little bit a matter of taste somehow.
Okay.
I like ours.
Okay, do we have any other questions or comments? Okay, that not being the case, let's thank Michael again.
Thank you. Thanks for listening.
All right.